Alright guys, I wasn't planning on having to be out today, so this is a real quick and simple summary of electromagnetic radiation. This is what we were working on last class. It's talking about how we can look at light as waves, and because of that we can characterize it by both its wavelength and its frequency. You saw a chart like this similar to the one that we talked about last class. You can see there with the wavelength size that radio waves are some of your largest waves, while gamma rays are some of your smallest. The visible spectrum falls more on the smaller size of the wavelength. We can see that it's in like 4 times 10 to the negative 7th to 7 times 10 to the negative 7th. And so that falls from Roy G. Biv, with red being the largest wavelength and the violet being the smallest. So we talked about how wavelength and frequency relate to one another. That wavelength is the distance between two peaks or troughs in a wave. So how far it takes to go from one point on your x-axis all the way till you reach that same point again. While frequency, and you can see that written as the crazy V, or you can write it as an F, is how many waves would pass through a given point in space per second. And then the speed of light is a constant, 3 times 10 to the 8th meters per second. And that's something that would always be provided for you. So there's your nice little triangle relating frequency and wavelengths to one another. Frequency tends to be written in hertz or 1/2. You do have to use the lambda, the wavelength, in meters. So if you're given nanometers, you have to convert it back. And then speed of light is in meters per second. So there's another picture kind of giving you an idea of how the wavelengths, what they're more related to in terms of everyday life. And then you also have the hertz given to you, the frequency, and how that those are inversely related to one another. So an FM radio station broadcasts at 99.5 megahertz. Calculate the wavelength of the corresponding waves. Because this is in megahertz, you're going to have to convert it from mega to just regular hertz, which would be multiplying it by 10 to the 6, since 1 mega unit is equal to 10 to the 6 base units. Since we're solving for wavelength, we would want to take speed of light over our frequency. So there's your speed of light, there's your frequency. We divide the two, 3 sig figs in your wavelength, in your frequency, so you want 3 sig figs in your wavelength. And if you want to write frequency as an F, that's fine with me. It does not matter. So you can see that the wavelength for a radio broadcast is pretty long. What we're going to talk about next is the relationship between matter and energy. And all of this should help you with the lab that we were working on today in class. That matter and energy were basically discrete entities. They were two separate things. Matter was particles, and that if you were a light, you were a wave, but matter couldn't be wave, and energy couldn't be particles. And Planck came along and decided to say, I don't know about this. What you were seeing today with the colors of light that were being emitted by the flame test was what he called quantums of energy being released. You see the absorption part. That was what you were doing when you were putting the flame into, or the wooden splint into the Bunsen burner flame. And then the emission is what color of light you were seeing as the photons were returning back to their ground state. Delta E refers to an energy change. It does not matter whether that energy change is positive or negative. In terms of what we're going to be looking at right now with relating energy to wavelengths. Know that when you go from a lower energy level to a higher energy level, you have to have an absorption of energy. And that when you are going from a higher energy level back down to a lower energy level, you're going to be having an emission, a release of energy, so it would be negative. Delta E is related to your frequency by the Planck's constant that we talked a little bit about on that assignment I gave you in class. And because we can relate frequency to the speed of light and wavelength, we can also relate energy to our wavelength. As your frequency increases, the amount of energy would increase. As your wavelength increases, the amount of energy would decrease, since those two are inversely proportional. H is a constant. That too would always be provided for you. We've already seen how speed of light is a constant. So in terms of this part of the equation, the H and C, that's always going to be the same values. It's just going to be the wavelength that basically is going to have an impact on your energy. Just like frequency is the only value that truly is going to have an impact on your energy when delta E is equal to H times the frequency. And so V and lambda, the frequency and the wavelength, are just what they were previously. So there's another triangle for you to look at, the relationship between delta E and wavelength. I did not give you a triangle for delta E and frequency because it's a linear relationship. That one's pretty straightforward. There's no fraction. So we now have a relationship between our light and energy, and then Einstein came along and related energy to mass by saying that if you looked at it as a stream of particles and you know the energy associated with those particles, you should be able to determine the mass of those particles, that the energy is equal to the mass times the speed of light squared. So particles can act like waves, and waves can act like particles. And Broglie was the one that put this relationship together as a whole by looking at the relationship with momentum and what Einstein has come up with. And if we have that concept, and we know that energy is also equal to the frequency times Planck's constant, we can put these two together and see what the relationship is between wavelength and mass. I do not expect you to derive this, but I did want you to know where we were putting these two entities together from. So the wavelength of any particle is equal to Planck's constant times the mass of that particle in kilograms times its actual speed, velocity in meters per second. Note that you have to have wavelength in meters, and then again you have to have your velocity in meters per second. How that all works out with the units with joules: 1 joule is equal to 1 kilogram meters squared per second squared. So by making it joules times seconds as Planck's constant, that cancels out one of your seconds. That's why we're short one over here. Diffraction, we saw this a little bit when you were looking through the glasses today, results when light is scattered from a regular array of points or lines. That's when we get those pretty little patterns. What we see with elements is that they produce these diffraction patterns when they're X-rayed, and that you wouldn't see patterns like this if the atoms and ions weren't able to move like waves traditionally do. So this was just kind of another bit of evidence supporting the idea that matter can act like it normally does as particles, but it can also exhibit properties of waves. And so what we see is that when you do an X-ray of sodium chloride, you get kind of a crazy diffraction pattern on the screen. And when you see the bright spots, it's because the waves have lined up together. And when you don't see the bright spots, when you see darker spots, it's because they are out of phase with one another. So I've talked about how you can look at the energy of a photon in terms of wavelength, and you can look at the mass of a photon in terms of wavelength. So if matter can have properties of waves and particles, well then light can have properties of mass, and it can have properties of waves. Blah, I can't talk today. And so if you have anything that you have a wavelength for, you can determine its energy. And if you have an energy value, you can determine its mass. You can use all these kind of interchange together. So when I was working in my labs, we would have to be really careful with the UV light we would use to look at our gels. Because, yes, a single photon of UV light has enough energy to mutate a strand of DNA. That's why you always want to be careful how much UV light you're exposed to. That's the big issue with the ozone layer and how it's providing us with greater amounts of UV light that we're being exposed to through the sun. What is the energy of a single UV photon and a mole of UV photons having a wavelength of 25 nanometers? Again, you can't leave your wavelengths in nanometers. You have to convert them to meters. 1 meter is equal to 10 to the 9th nanometers. So if I change the nanometers to meters, I get 2.5 times 10 to the negative 8th. If I substitute in my Planck's constant and my speed of light, I cancel out my meters, I cancel out my seconds. I'm left with the energy that would be needed per photon that would be present for that wavelength of light, 8 times 10 to the negative 18th. We don't tend to work with particles in terms of individual photons or individual atoms because it's really hard to get a hold of something in that context. So if I want to know what the energy is for a mole of UV photons, I would take the energy for a single photon and use Avogadro's number to relate 1 photon to a mole of photons. And we see that the energy here for 1 UV photon that has a wavelength of 25 nanometers is 4.8 times 10 to the 6 joules per mole of photons. So we're talking 4.8 megajoules of energy that is emitted for a mole of photons that we're exposed to. That's a fair amount of energy. And I believe this is where I'm stopping at with you guys. Well, no, I'm going to do one more after that. Sorry. It takes 208.4 kilojoules of energy to remove a mole of electrons, and we can look at electrons like photons, from an atom on the surface of a rubidium metal. How much energy does it take to remove a single electron from an atom on the surface of a solid rubidium? And what is the maximum wavelength of light capable of doing this? So this energy here is needed to remove 1 mole of electrons. We want to know the energy for 1 electron. So if we've gone from a photon to a mole of photons, we can go from a mole of electrons to a single electron with Avogadro's number. And we get that the amount of energy that would be needed to remove 1 electron is just a little bit smaller, 3.62 times 10 to the negative 22nd kilojoules. If we want to know the wavelength that would be capable of doing this, and we know the energy that would be needed to do this, we can rearrange our equation relating energy and wavelength to solve for wavelength in terms of energy. We substitute Planck's constant, we substitute the speed of light, we substitute our energy. I want you to notice that I changed this from kilojoules to joules so that the joules units would cancel out. If you are using a constant, you've got to have common units to be able to make that conversion. And when I do the multiplication and division through, I get that the wavelength I would need is 5.742 times 10 to the negative 7th meters. Now, I put this in nanometers because this is in the visible spectrum. So this is something that regular light would be capable of doing. Visible light would be capable of generating enough energy to remove a single electron from rubidium surface. And then the last part we're going to do is involving de Broglie's principle, that neutron diffraction is used to determine the structure of molecules. Calculate the velocity of a neutron with a wavelength of 75 picometers. I do not expect that you know the mass of a neutron or the mass of a proton or the mass of an electron. And on your homework, I've given you that information. So if the wavelength is equal to Planck's constant over mass times velocity, I should be able to find velocity by rearranging the equation so that Planck's constant remains in the numerator, and basically wavelength and velocity have switched places. Planck's constant is still the 6.626 times 10 to the negative 34th. The mass of a neutron, this is just something I looked up in your book most likely. It's fairly easily constant to determine. 1.67493 times 10 to the negative 27th kilograms is the mass of a single neutron. And then I had to convert picometers to meters. 1 meter has 10 to the 12th picometers. So converting that to meters gives me 7.5 times 10 to the negative 11th meters. I'm going to divide 6.626 times 10 to the negative 34th by these two quantities. And I get that the velocity of a neutron with that particular wavelength is 5,300 meters per second. I did 2 sig figs for this one because the wavelength was 2 sig figs. All right. And so I'm going to stop there. That's going to help you get started a little bit, I believe, at least with the second part of your lab, in terms of calculating the energies of the wavelengths of light that you observed in your flame test. That also should get you through the first homework assignment in your new homework packet. And the PowerPoint slides for this will be posted up on Classroom, so you can use those as well if you prefer. And I will go over all of this with you guys again on Friday if you have any questions.